Autodata, an agentic data scientist, to create high-quality synthetic data by FAIR at Meta, June 2026. So if you are fine-tuning models or building reinforcement learning pipelines or honestly just trying to push the boundary of what an LLM can do, you already know the frontier isn't human data anymore.
Right, yeah. It's all synthetic data now.
Exactly. It's synthetic data.
Yeah.
But you've probably also noticed this wall we're hitting. Standard synthetic generation, where you just prompt an off-the-shelf model to spit out a million practice questions. It's yielding severe diminishing return.
Oh, absolutely. The quality just degrades.
Yeah, and that's where this paper comes in. It introduces Autodata, specifically this framework they call Agentic Self-Instruct. And here on AI Paper Slop, we like to cut straight to the core insight. So instead of treating dataset creation as this static one-shot prompt, the researchers set up an AI agent to act like a lead data scientist.
Which is such a brilliant shift in perspective.
It really is.
Yeah.
This agent iteratively generates, evaluates, and then refines training examples by testing them against two models.
Yeah.
So you have a weak solver, which is the model we actually want to train, and a strong solver that acts as an oracle.
Mm-hmm.
And the magic happens when the agent finds this exact Goldilocks zone of difficulty for reinforcement learning. So by converting upfront inference compute into highly calibrated data, they basically took a 4 billion parameter model and made it beat a massive 397 billion parameter model on expert legal reasoning.
Yeah, that blew my mind when I read it.
Right. So we are going to break down the exact architecture of this multi-agent loop, look at 3 really surprising experimental domains, and explore how the researchers even used an evolutionary algorithm to optimize the agent itself.
Yeah, because it fundamentally changes the math of model training, For a long time, the community treated synthetic data generation as a volume game. Just generate more chain-of-thought examples.
Just throw more tokens at it.
Exactly. But this paper proves that data generation is really an iterative engineering problem. You get exponentially more value by spending your compute budget on a multi-agent bit to craft, say, 1,000 perfect examples rather than generating 1 million mediocre ones.
So to understand how a 4 billion parameter model punches roughly 100 times above its weight class, we really need to look under the hood at the specific architecture they built. We've got a main orchestrator LLM directing 4 specific subagents. Walk us through how this assembly line actually functions.
Sure. So the process starts with the challenger agent. Its job is to ingest grounding data, say a dense computer science paper or a complicated legal ruling, and then it generates a training task.
Okay, so it writes the actual tests.
Exactly.
Yeah.
That task includes the question, a reference answer, and a highly specific grading rubric. Next, you have your 2 solvers. The weak solver is the target model you are actually trying to improve.
Which in the paper's experiments is typically Quinn 3.54b, right?
Right, the 4B model. Then you have the strong solver, the oracle model, which is the massive Quinn 3.5397b. And finally, sitting above the solvers is the judge, or the verifier agent.
So if I'm tracking the workflow here, the challenger creates the question, the judge probably does a sanity check, and then both the weak and strong solvers try to answer it.
You got it.
But the value isn't just in, gathering their answers, right? It's what the judge actually does with those results.
Yeah, that is the critical iterative loop. The judge evaluates both solvers' outputs against the challenger's rubric. But here's the mechanism that makes Agentic Self-Instruct so powerful. If the weak solver gets the answer right too easily, or if the strong solver fails it entirely, the judge rejects the question.
It just throws it out.
Well, it sends the challenger back to the drawing board with explicit feedback. It forces the challenger to refine the prompt until a very specific performance gap is achieved between the 2 models.
Okay, I look at this like a personal trainer designing a workout routine for an amateur athlete. The challenger is the trainer. The amateur is our weak solver. If the trainer designs a workout that is, way too easy, the amateur coasts through it and doesn't build any new muscle.
No gains.
No gains. But if the workout is impossibly hard, the amateur just gets crushed under the barbell and learns nothing. So the trainer brings in a professional athlete, the strong solver.
I like this analogy.
Thanks. So the trainer adjusts the weight on the bar until the professional can lift it cleanly, which proves the workout is technically sound, but the amateur struggles and fails. That failure point is exactly where the growth happens.
And translated to machine learning, that struggle is your gradient signal. The strong solver's success guarantees that the task is solvable, factually grounded, and logically sound.
Right.
And the weak solver's failure proves the task sits just past its current capability frontier. That provides the exact contrast needed for a reinforcement learning algorithm to optimize the model's weights.
Okay, so we have the workout routine established. But how does the system adapt when you feed it a data set where the baseline information is just fundamentally too easy? Like, let's look at their first major experiment, which focused on computer science research papers.
Yeah, so for this, the researchers used the S2ORC corpus, the Semantic Scholar Open Research Corpus, processing over 10,000 computer science papers. They started by testing standard synthetic data methods.
What they call co-self-instruct, right?
Exactly. Co-self-instruct, where you just ask an LLM to generate reasoning questions from the text. The problem was that these standard prompts produced incredibly surface-level questions.
Like, summarize the main contribution of this abstract, or what data set did the authors use?
Yes, high-level summaries that require almost no deep reasoning. As a result, the weak solver was scoring around 67.7% right out of the gate.
Wow, so almost a B- without any training.
Right. And if you are running reinforcement learning and your target model is already getting the answer right 2/3 of the time before you even start training, your optimization ceiling is incredibly low. There just isn't enough error to learn from.
So this is where the agentic loop steps in. And reading the paper, it didn't just tweak the questions once or twice and call it a day.
No, not at all. It took an average of 6.59 refinement rounds for every single accepted question. The judge agent aggressively rejected questions that were too easy.
Because the weak model kept passing them.
Exactly. In fact, during the pre-acceptance rounds, 80% of the rejections occurred specifically because the weak solver scored too high. The loop forced the challenger to abandon those high-level summary questions. Instead, it had to start generating questions about specific algorithmic steps, multi-step mathematical derivations, and ablation details.
Meaning questions about why a specific component of an architecture was removed or altered.
Exactly. Deep analytical questions.
So the agent is basically acting like a brutal thesis advisor. It filters out all the GIMs and forces the student to prove they actually understand the math. What did that do to the scores?
Well, the weak solver's average score plummeted from 67.7% down to 45.8%.
Ouch.
Yeah, but here's the crucial metric. The strong solver's score actually rose from 69.6% up to 77.2%.
I have to push back on this, though. If the weak solver's score drops that dramatically, how do we know the challenger agent isn't just generating like obscure pedantic trivia to artificially create a performance gap?
Wait.
Like if the agent asks, what is the third word of the fourth footnote on page 12?
Yeah.
The weak solver will fail.
Yeah.
That doesn't teach it how to reason.
That is the exact trap you would worry about with an automated curriculum designer. But the strong solver's performance is the built-in safeguard against trivia.
Oh, because it has to pass the strong solver too.
Right. If the questions were just random noise or pedantic formatting traps, the strong solver wouldn't be able to reliably answer them either. The fact that the 397 billion parameter model score increased to 77.2% proves that the questions reward deep, generalizable reasoning.
That makes total sense.
And the ultimate proof is in the training results. When they trained the 4B model via GRPO on this highly discriminative data, it yielded massive verifiable performance gains on held-out test sets compared to models trained on the standard CAUT data.
So in the realm of computer science, the agent's job was to take an easy test and make it brutal. But what happens when the baseline data is already so incredibly dense and complex that it completely paralyzes the model?
That is the exact wall they hit when they moved to the second experiment on legal reasoning.
This is where the Autodata framework really shows its dynamic range, because they used court opinions from the pile of law and evaluated the models on PR Bench, which tests professional legal analysis. And when they used standard prompting to generate legal questions, they created tasks that were hopelessly difficult. The weak solver averaged just 15.9% accuracy. And worse, on many of the training rollouts, it scored a flat 0.
Yeah, and for anyone listening, if you've ever dealt with reinforcement learning, specifically GRPO or group relative policy optimization, you know that a score of 0 across the board is a mathematical death sentence for your training run.
It is entirely fatal. To explain the mechanics of that, GRPO works by sampling a group of different outputs or rollouts for the exact same prompt, right?
Yes.
It scores all of them, calculates the mean score of the group, and then updates the model's policy to favor the outputs that performed better than the average.
But if every single rollout scores 0...
Your mean is 0,
Yeah.
and the relative advantage of every output is 0.
Right, there is no variance. And without variance, there is no advantage signal. The mathematical gradient just vanishes, and the model doesn't update its weights. You are literally just burning GPU compute to learn absolutely nothing. Precisely. And the agentic loop recognized this failure state immediately. The judge agent saw that the variance was too low and sent feedback to the challenger telling it to dial back the complexity.
Oh, wow. So it actively made it easier.
Yeah. It instructed the challenger to push for shorter, realistic application-style questions rather than these dense, multi-statute textbook queries that were paralyzing the 4B model.
So it actually narrowed the gap between the two models and made the questions easier, but in a very targeted way.
It pushed the weak solver's average up from 15.9% to 28.3%. But the critical metric is the standard deviation across those rollouts, which increased from 7.93 to 12.63.
So it created variance.
Exactly. It took an impossibly sheer cliff face and carved a slope into it. It spread that performance gap over a usable variance range, so the GRPO algorithm actually had a signal to grab onto.
That right there is the aha moment of this entire paper. The true goal of Autodata isn't simply difficulty. The goal is learnability.
Yes, learnability.
It is sculpting the reward landscape. If the wall is completely sheer, the model can't climb it. The agent carves the handholds based on the model's exact current height.
And the payoff for engineering that gradient is staggering. After the Quinn 3.54B model was trained on this perfectly calibrated legal data, it scored 0.441 on the PR bench legal test.
Wait, 0.441?
Yeah, which beat the 397 billion parameter baseline, which only scored 0.404. Let that sink in. A 4 billion parameter model outperforming an expert model roughly 100 times its size purely because the synthetic data was autonomously engineered to be maximally learnable.
It's an incredible result. Now, we see the agent adapt to both easy extremes in CS and hard extremes in law. Let's look at one more domain. Scientific reasoning, dealing with complex math and physics, because here, the agentic data revealed a massive hidden bottleneck in how these models actually fail.
Yeah, for this, they used the Principia dataset, which covers heavy scientific reasoning over complex mathematical objects. Unsurprisingly, training the 4B model on the agentic data improved its average performance by 3.20%, outperforming a combined training dataset that was twice as large.
But the real story in the scientific reasoning section is the attribution analysis. The researchers dug deep into the logs to figure out why the base models were failing before training and what exactly the new data fixed.
The most fascinating discovery here was the truncation rate. They gave these models a massive context window for reasoning, a 65,536 token budget.
Which you would assume is plenty of space to solve a physics problem.
You'd think so, yet the base 4B model had a truncation rate of 23.75%. Nearly a quarter of the time, the model was hitting its token limit and getting cut off before it could even finish its chain of thought.
Wait, so you're telling me it was rambling for 65,000 tokens and still not arriving at a final answer? That is a staggering amount of wasted text.
It really highlights a flaw in base models. It wasn't necessarily that the model lacked the underlying mathematical capability to solve the equations. It simply could not route its reasoning efficiently.
It just got lost in the weeds.
Yeah, it would go down dead ends, restate the premise over and over, or generate overly verbose derivations. But after training on the Agentic Self-Instruct data, that truncation rate plummeted down to just 4.09%.
How exactly did the data fix that? Was the challenger agent specifically telling the model to be shorter?
Not explicitly, no. It was an emergent property of the rubrics the agent designed. To separate the weak and strong solvers on complex math, the challenger's rubrics had to heavily reward direct, mathematically sound, step-by-step logic.
Okay, so if it rambled, it didn't score well.
Right. When you run reinforcement learning against those strict logical rubrics, the model naturally learns to prune its meandering conversational filler. The researchers concluded that around 50% of the accuracy improvements were simply because the model learned to organize its thoughts and execute the math concisely before the token clock ran out.
So you aren't just injecting new facts into the model. You are teaching it operational efficiency.
Exactly. You're teaching it how to think cleanly.
Okay, so the inner loop is clearly a powerhouse. The challenger, the solvers, the judge, they create an incredibly refined dataset. But the FAIR researchers didn't stop there. They asked a brilliant question. What if we let an AI optimize the data scientist agent itself?
Yeah, this brings us to the meta-optimization phase. They built an outer loop using an evolution optimization framework. Normally, human engineers sit around tweaking the system prompts for the challenger and the judge, trying to get them to behave.
Which is tedious.
Very. So here, they treated the agent's system prompt and underlying Python scaffold as code and let a separate LLM iteratively rewrite and improve it.
So we have an AI analyzing the AI data scientist writing code to make it better at training another AI. It's almost dizzying.
It's turtles all the way down. Over 233 iterations, this meta-optimizer analyzed the failure trajectories of the inner loop. It looked at exactly why certain generated questions failed to separate the weak and strong solvers. And then it implemented code diffs to the system prompts to prevent those failures in the future.
What kind of performance jump are we talking about from optimizing the optimizer?
It increased the validation pass rate of generated questions, meaning the percentage of questions that successfully hit that perfect Goldilocks zone of difficulty on the first few tries from 62.1% to 79.6%.
That is a massive jump in yield. You are saving so much compute by not having to throw away failed questions. What exactly did the meta-optimizer change in the prompts to get that almost 18% improvement?
It made several automated discoveries that would take human engineers weeks to dial in. First, it added strict rules to enforce paper-specific knowledge.
How so?
Well, it realized the weak solver was occasionally faking its way to a high score by outputting generic, plausible-sounding machine learning concepts. So, the meta-optimizer explicitly instructed the challenger to test details that could only be answered by reading the specific grounding paper.
That makes perfect sense. It closed the generic knowledge loophole.
Second, it recognized parsing errors. So it enforced strict JSON formatting for all the rubrics, ensuring the judge could always read them computationally. It also added self-tests to prevent what we call context leakage.
Context leakage being the spoiler effect, right? Where the challenger accidentally embeds the solution or a massive hint into the prompt itself while trying to formulate the question.
Exactly. The meta-optimizer added a step for the agent to check its own work and ensure the premise didn't give away the punchline. But the most counterintuitive and crucial discovery was about the grading rubrics themselves.
Oh.
The optimizer completely eliminated negative rubric weights.
Wait, taking away negative penalties feels super counterintuitive. Like, if a model hallucinates a fake legal doctrine or makes a massive arithmetic error, you would think you'd want to slap it with a -5 points on the rubric, right? Why did the AI discover that penalizing errors breaks the system in practice?
It comes down to the brittle nature of LLM as a judge systems. The meta-optimizer realized that negative weights frequently misfired on nuance. For instance, the strong solver might provide a highly complex, nuanced answer that includes a hypothetical example. The judge agent might misinterpret that hypothetical as a hallucination and trigger a massive negative penalty.
Ah, so it accidentally punishes the smart model.
Right. That destroys the strong solver's score, ruins the separation gap, and causes the whole question to be rejected. By capping all criteria at a +7 and framing everything affirmatively, for example, instead of -5 for hallucinating, using +2 for successfully avoiding known legal contradictions.
The rubrics became incredibly stable and reliable.
Exactly. Positive reinforcement worked better.
It is fascinating that the evolutionary algorithm figured out that positive reinforcement rubrics evaluate more reliably than punitive ones, purely through trial and error over hundreds of iterations. It really highlights how difficult it is to manually prompt engineer these complex agentic systems. The AI found optimizations that humans thought were counterintuitive.
And that is the broader takeaway from Autodata. Human intuition about what makes a good training dataset is often flawed. We think in terms of static difficulty. The AI thinks in terms of dynamic gradients and reliable reward signals.
Let's bring all these threads together. For everyone listening, whether you're building production models, curating domain-specific datasets, or just trying to stay ahead of the research curve, what does this paper signal for the future of AI workflows?
The core thesis is that the era of static, single-prompt synthetic data generation is ending. We are transitioning to automated, agentic data science workflows. The paper proves that if you throw massive amounts of inference compute at the creation phase, letting agents debate, test, and mathematically refine the data against your specific target model, it yields exponentially better downstream performance.
You stop trying to guess what data your model needs.
And you let an agent empirically discover it.
You walk away from this analysis understanding the profound difference between merely hard data, which might just be unlearnable trivia or an impossible sheer wall, and discriminative, learnable data that is meticulously tailored to carve handholds into a model's exact capability frontier.
You are no longer just curating text. You are engineering the learning gradient itself.
It's a brilliant paradigm shift. But I want to leave you with a final concept to chew on based on a brief note in the discussion section of the paper. We just spent this deep dive looking at meta-optimization, where an outer loop optimizes the data scientist agent. But what about co-improvement? Right now, the challenger agent creates the data set, and then later, the weak solver is trained on it in a separate phase. Imagine a near future where this challenger agent and the solver model are training and updating their weights simultaneously.
Oh, that would be wild.
An endless, automated, evolutionary arms race of intelligence happening entirely in the latent space. Every single time the solver gets a tiny bit smarter and updates its weights, the challenger instantly detects the new capability and learns how to generate the exact highly calibrated puzzle needed to push it to the next level. That is the true frontier of synthetic data.